In this video, we're going to take a look at power, resistivity, and thickness of wire, which is often indicated by wire gauge. So let's start off with an example of the incandescent light bulb. I better label this light bulb because it's kind of, I don't know if you think it's a jellyfish or all right, so Thomas Edison, his business was to refine the light bulb, although patents for light bulbs have been around for 30 or 40 years before Edison. And essentially we have a metal package and then a glass bulb in order to let the light out, evacuated primarily. Evacuated since, to avoid gases like oxygen from rusting this metal filament. So current goes in, travels up, goes through the filament, and comes back out again. And let's suppose a pretty common light bulb was 60 watts. Now, LEDs are the way to go for sure. They last much longer and they're much more efficient. This 60 watt light bulb, it turns out that for this incandescent light bulb, you get about 5% of the energy that goes into the light bulb comes out as light. And 95% heat. So very, very inefficient. Although if you're trying to bake something in your easy bake oven, this is clearly the way to go. So let's think about that 60 watts. So normal household current is delivered in a 120 volt package. With alternating current. So since power equals voltage times current, then we can make a substitution. We put in 120 volts for V and then power. And so then that tells us how much current this draws. So 60 watts equals 120 times I. And so I turns out to be 0.50 amperes. Okay, great. Now, really what is happening here is that the discovery that that when you pass a lot of current through wires, they get hot and they might get hot enough to glow. And so that's really where the incandescent light bulb comes from. And probably discovered by accident of somebody making a mistake in the lab, somebody shorting something out. So in the process, right before the damage occurred, stuff was probably glowing red hot. But this can happen to anybody. I accidentally set aluminum on fire in my lab once. So, all right. So 0.5 amps. Now, this is heated up really hot. So we're coming in at around 2000 degrees C. Right, super hot. So let's think about what would go into this filament. How long should it be? How thick should it be? And we know that resistance, well, let's go ahead and figure out what this resistance is going to be. So Ohm's law says V equals I times R. And now we have 120 equals 0.5 times R. We'll divide both sides by 0.5, and so R is going to be equal to 240 ohms. So we need to have resistance. And so when we think about resistance equals resistivity times the length divided by the cross-sectional area, then the skinnier the filament is, the more resistance it's going to have because it's inversely dependent on the area. And for a wire, we would probably assume that the area is the cross-sectional area, so pi r squared. All right, well, we know that our light bulbs are made of tungsten. And of course, we can look up the resistivity for tungsten. And so I'm just going to do that really quick. Okay, so we get about 5.6 times 10 to the minus 8. And that's in ohm meters. Okay, now what about this length? Well, usually the filament is kind of coiled up a little bit in order to distribute as much light as possible. And but even at that, it's not going to be terribly long. So let's assume L equals, if we stretch this all the way out, let's suppose it equals 1 meter. Okay, find the wire gauge. Okay, terrific. Now, we know resistivity depends on temperature. So we're going to have to make a modification. And so to show the temperature dependency of resistivity, we can do something like this. We can write the resistivity at room temperature and then multiply this by the factor 1 plus alpha times delta T, where delta T is the temperature above room temperature. And so 2000, obviously room temperature is going to be around 20. So let's go ahead and plug this in and see what we get for resistivity. So this is going to be 5.6 times 10 to the minus 8. And then we multiply 1 plus, and the temperature coefficient for tungsten is 0.0045. And then 20 minus 2000 is going to be 1980. Okay, and we'll put that all together. So let's go ahead and see what our calculator has to say about that. Okay, we'll do what's inside here first. So 1 plus 0.0045. Just double check something really quick. Right. Times 1980. Okay, so what's in here is 9.91. That means that the resistivity is going to be about 10 times greater at this temperature than it was at room temperature. So now we can multiply that by 5.6 E minus 8. Great. So 5.55 times 10 to the minus 7 ohm meters. Okay, terrific. Now we assumed a length of 1 meter, so, and we want R to be 240. So if we write down this equation again, now we make some substitutions. So R is supposed to be 240. The resistivity is 5.55 times 10 to the minus 7. And then the length is 1 all over the area. So this gives a cross-sectional area. That's going to be very small number. So we multiply both sides by A, and we're going to take this number and divide by 240. And it's a very small number, but of course we're talking about the cross-sectional area of a filament in a light bulb. So it's going to be a very small number. And that's in square meters. Now, if we're going to find the thickness of the wire, which is diameter, we recognize that the area for cross-sectional area for a wire is going to be that of a circle. And I could use pi r squared for that, but since I'm looking for the denominator anyway, I'm just going to use pi d squared over 4, because I think that's a little bit less problematic than having to remember to multiply by 2 on the end. Okay, so we're going to multiply both sides by 4, divide both sides by pi, take the square root of this number, and again, we get a very small number. But that's in meters. So we can move the decimal point a couple of places, and so that's going to be 0.0543 millimeters. That's pretty tiny. Let's go see what the American wire gauge has to say. So I had included the American wire gauge on Canvas, so you don't have to dig for that. It's pretty easy to find. So I'll share my screen. We can go take a look at that. Right. So I'm interested in looking at millimeters here, and you can see as the gauge goes up, millimeters goes down, and so I'm looking for about 0.005. Yeah, so a little bit less than this. The smallest thing was gauge 40. Okay, great. Well, this is a quiz question. Oops, I would never didn't wind up sharing. So there you go. This is the American wire gauge, and down here around 40. That's where things can. So we'll go back and we'll take a look. So yeah, probably about gauge 40 sounds about right. Yeah, this is the quiz question. So good luck with that, and I hope everything works out for you.